This video studies functions for which the input is recoverable from the output. These functions are called inverse functions, and they are discussed on pages 163 up to 167 of the book. We already saw one example in the previous video, but now we take a slightly more complicated one. In this example, we have our set D equal to the whole set of real numbers, and we define the following function which assigns the value x squared to each x. Now probably you know how the graph of this function looks like. It's like this. Now clearly this is a function because to each input value x we assign precisely one output value x squared. However, if we want to go back, so we start with an output value y, then it's not clear what was the input value. It can either be this one or, in fact, minus x. And we simply do not know which one was our original input. So in this case we cannot recover the input from the output. However, if we change our set D a little bit, so suppose we make it into the positive reals, suppose that we know that our inputs are non-negative, then clearly we can do it, because then we can recover from this y, we get back one original x. So we can go back, in this case, from y. So what is now the characteristic of a function which has the property that we can recover the input from the output? Well, this property can be mathematically described as follows. So it's the following definition. A function defined on some set D with values in R is called 1, 1 if for each y in the image of our set D there is precisely one value x, of course in the set D, with the property that y is equal to f of x. And the consequence of this 1, 1 property is obviously that going back is a function. Now this going back rule function is called the inverse function. We denote this inverse function by f minus 1. So this is clearly not equal to 1 over f. So this is a warning. We have to specify, when we specify a function, we have to specify on which set it is defined. Well, clearly going back means that we can only go back from realized values. So we have that the domain of this inverse function, denoted by d f minus 1, is equal to the image of our original function of the set D. We cannot go back from a non-realized value. What will happen in our specific example of the function which is equal to y is equal x squared. Let's look at it again. So now we only take the domain equal to the positive reals. So we only consider the function on that part of the space. So we'll just draw it. So what we do get in this case, so we have our set D equal to the positive reals. The image of the positive reals is equal to the positive reals. Our original function assigns x squared to x, and the inverse function assigns y. Well, what do we get if we go back? If y is equal to x squared, then x is equal to the square root of y in this case. So we go back by taking the square root. And we can note it also by y to the power 1/2. Now there is quite some nice property attached, which you can easily see in a picture. That suppose that we start with our x in D and we apply the function f of x is equal to y. So we go one way. Since the inverse exists, we can go back by the function f minus 1. So we get the inverse function applied to the point y is equal to x. And if we go first according to f and then back according to the inverse function f minus 1, then we come back to the original point. Now obviously if we start in y in the domain of the inverse function, which is equal to the set of realized values, the image of our set D under the map F, then by using the inverse function we come to point x equal to f minus applied to y. We can then apply again the function f, so we come back according to f minus 1 and we go again the other direction by applying f, and we come back to our original point y. This is in fact the composition of functions, and I hope you have read in section P5 how you make such a composition. So this is a feature that if you put first f and then f minus 1 to the result, we come back to our original point, and the same happens if we first start with f minus and then apply f, we come back to the original point as well. Is it easy now to make a graph of this inverse function? Well, you can do it by interchanging, in fact, the x and y axis. So we swap y and x. What do you get? So we put y now on the horizontal axis, x on the vertical axis, and we swap these two. Then you get this picture. This is now the function, as we said, x equals square root of y. But of course, in general, we do not we denote input variables by x and output variables by y. So we replace y by x and x by y, and then we get also y equals square root of x. So in fact, what we denote by the inverse function, in fact, is that if we start with the function f of x equal to x squared, then we get the inverse function equals to the square root of x. Of course, on the special domains that we consider.